Hey there, folks. Here's part one of my day 28 lecture. This is on 12.1, the simple linear regression model. Chapter 12 is about linear regression, and we'll be covering a few sections in chapter 12, 12.1, 12.2, and briefly 12.5. And this lecture is on the first section, 12.1. So the goal with linear regression is to model the relationship between a pair of numeric variables. Okay, so notice what I just said. This is between a pair of variables, and specifically, they both have to be numeric. So, for example, let's say you wanted to predict someone's weight from their height. Or let's say you were building a new metallic alloy, which had a certain amount of iron in it, and you were trying to predict the compressive strength of the alloy from the amount of iron in the alloy. Or let's say you were trying to predict what sort of income you're going to earn based on your GPA. These are all examples of paired numeric data. Now, not all paired numeric data follows a linear relationship. So here are some various apparent relationships. The first one looks linear, right? So this is something of the form y equals mx plus b. That's a linear relationship. And that's the type of relationship for which linear regression analysis is important. But there might be other relationships between numeric data. For example, a quadratic relationship. So this is not linear. Nevertheless, as I'll explain shortly, you can transform this into a pair of variables that do have a linear relationship. How about something that is oscillatory? And I actually used y equals sine x to generate this plot. And you could, for example, imagine that the y value is temperature and the x value is time. And this is the temperature over the course of the day. So it increases and reaches a peak, let's say in the middle of the afternoon, and reaches a minimum, let's say in the middle of the night, and then does the same thing over again the next day. So again, this is not linear. Finally, we have an example of paired numeric data with no apparent relationship. So in this case, there's nothing that you can really do. Not regression analysis, not a transformation. So we won't be handling such cases. And to be clear, when I say linear relationship, I mean a relationship of the form y equals a plus bx, or mx plus b equivalently, if you want to use the letters m and b instead of the letters a and b. And I claim that linear relationships are the most important non-trivial relationships between a pair of numeric data. And here's why. There's a few reasons why. For one, other relationships can often be reduced by way of some transformation to linear relationships. For example, in the quadratic case, what if you just take the square root of all your y values? Because if y is equal to x squared, well, then the square root of y is equal to x. So square root of y and x are a new pair of variables with a linear relationship, which would then be amenable to linear regression analysis. Or even more generally, suppose that y is some power of x, any power, it doesn't matter. So if y is equal to a times x to the b, with a and b being unknown but constants, then if you take the log of both sides of this equation, you find that ln y is ln a plus b times ln x, and you now have a new pair of variables, ln y and ln x, that have a linear relationship. So once again, by way of a transformation, you have been able to furnish a pair of linearly related variables. Finally, sometimes you don't even have to do a transformation, but just restrict your attention locally. For example, in the temperature versus time relation, if you just restrict your attention, say, to the hours between 12 noon and 3 p.m., you can locally approximate that relationship as linear. So once again, linear analysis would be appropriate in that local region. Okay, so I hope I've convinced you of the importance of linear regression analysis. So now let's take a look at our midterm 1 and midterm 2 scores. Hey, sorry, I had to pause the video because I wanted to make sure that I was using your midterm scores and not the midterm scores from my other section. So I just went into Excel and Canvas and R, and I plotted out a so-called scatter plot of the midterm 1 and midterm 2 scores for students in 4001. So somewhere on this plot, you should be able to find the point which contains your midterm 1 score on the x coordinate and your midterm 2 score as its y coordinate. Like, for example, this student looks like they got about 60% on both midterms. Let's see who. This student looks like they got just a little bit less than 80% on the first midterm, but got like 100% on the second. So good for that student. They made a good improvement in their score. Here's the code that I used to generate that. As I explained, each point has x coordinate equal to the midterm 1 score and y coordinate equal to the midterm 2 score. And we call such a plot a scatter plot. And you can code this in R or generate these in R via the plot command, where the first vector of input are the x values, the second vector of input are the y values, and these two vectors need to have the same length, of course, right? Because this is paired numeric data. In terms of terminology, we'll often describe the x-axis or horizontal axis variable as the independent or predictor or explanatory variable, and the y-axis or the vertical axis variable as the dependent or the response variable. So implicit in this terminology is that we are treating the x variable as the thing that we can control, since it's independent, and the y variable as the response to the x variable. Now, it may not in fact be true that your midterm 2 score depends on your midterm 1 score. For example, if you didn't study for midterm 1 but did for midterm 2, then the two might not have any relation. In fact, they both probably depend on the number of hours studied, which, so in that case, you might call hours studied a lurking variable. So just because we call x the independent or the explanatory variable, and we call y the dependent or response variable, doesn't mean that that is, in fact, the true relationship between those two variables. Now, notice that generally, unsurprisingly, students that did better on midterm 1 also did better on midterm 2. So there's a general upward trend in the scores. And we can fit a so-called linear model or least squares line via the LM command in R. So LM stands for linear model. And if I execute LM of midterm 2 tilde midterm 1, I get the following output. Notice, by the way, that you need to do the y variable tilde, the x variable, in contrast to the plot command. Like the order of the arguments in the linear model command is the reverse of that in the plot command. So the output of the linear model command in R are the two coefficients, the y-intercept and the slope. So that tells us what our regression line is. It's the line y equals 0.3590 plus 0.5382x, right? This is the slope, this is the intercept, and I can overlay this line on the scatter plot with the AB line command. In fact, you can even just stick the model directly into the AB line command. So doing so, we see our so-called regression line, our line of best fit. Now, in the next lecture, I'll explain exactly how we define best fit for least squares. For now, just know that it fits the data in some sense. And let me explain how to interpret it. So you should think of the y value that corresponds to a given x value so for a given x value, the The y value on the line is the predicted average value of y for the given value of x. So for example, let's say x is 1/2. So let's plug in 1/2. So this times 0.5 gives the predicted average midterm 2 score for students that get 50% on midterm 1. Right. You can even see where it is. In fact, let's see what it is actually. This would be 0.6281. So if you look for where x is 0.5, 0.6281 is the y value that's on the line above x equals 0.5. And moreover, if many students took this exam many times, among all the students that got 50% on the first midterm, the average midterm 2 score is predicted to be about 62.8%. So that's the interpretation of the regression line, the predicted average y value for a given x value. How about at the intercept? So, well, this is a prediction for a specific x value, namely x equals 0. So this is the predicted y value corresponding, or perhaps I should say predicted average y value corresponding to x equals 0. However, this may not be relevant. It may be that this is outside the scope of the model. So warning, this may be outside the scope of the model, particularly if there are no x values near 0. Now, did we have any x values near 0? It doesn't look, no. I don't see any near 0. It looks like the smallest was, what, like 0.3. So we didn't have any x values of 0. And in fact, if you think about it, it would be pretty hard to get a midterm score of 0 on one of my exams. Even if you guessed on every problem, you wouldn't get 0. And I was only including points in this scatter plot for students that did take both exams. So in the example at hand, the model predicts a midterm 2 score of 35% for students who got 0 on midterm 1, but no weight should be given to this prediction as it appears to be outside the scope of the model, as there are no x midterm 1 scores near 0. Okay. Finally, there's the interpretation of the slope. So the slope of the regression line gives the predicted change in the average value of y that corresponds to a 1 unit increase in x. So, for example, Now, it doesn't really make sense to increase x by 1 because the x values are all between 0 and 1. So an increase of 1 would be like way too big. That would probably be outside the scope of the model. So let's just increase it by 10%. So if, let's see, this follows from the fact that the slope is equal to delta y over delta x, so is equal to delta y when delta x is equal to 1. All right, so like I was saying, it doesn't really make sense to increase your midterm 1 score by 100% because that would put you beyond the scope of the model. What if you increased it by 10%? Well, the slope is, what did we say it was? 0.5382. So delta y over delta x equals 0.5382. So if delta x is 0.1, which corresponds to improving your midterm 1 score by 10%, then delta y would be 0.1 times 0.5382, which is 0.0532. So improving one's midterm 1 score by 10% predicts an average improvement in midterm 2 score of about 5.3%. Here, why don't you tell me what the predicted average midterm 2 score of someone who got 100 on midterm 1 is? So why don't you tell me that? And let's see, your answer should be what you get if you plugging in x equal to 1 to this gives that y is equal to this times 1, which is about 0.8972. So this says that students that got 100% on midterm 1, on average, were getting about 89% on midterm 2. That's what we just found there. Okay, cool. So here's some more terminology. You can have positive correlations. Those are correlations where an increased value of x predicts an increased value of y. And you can have negative correlations. That's where an increased value of x predicts a decreased value of y. So at top, we have positive correlations. And on the bottom, we have negative correlations. Also, the ones on the top are pretty strong. So I'm going to say those are strong. And the ones on the bottom, they're not as strong. So they're a little bit weaker. You can see the strength of the correlation is how close the data is to lying on a straight line. So let's see, got some examples here. Let's just do let me pick a pair of variables in the class survey. And Which pair of variables in the class survey do you think are likely to have a linear relationship? Like, let me look at them. What about video game hours and work hours? Do you think those are related? Here, let me just take a look at a plot of CS video games and CS work hours. Huh, could be. Yeah, it kind of makes sense. The people that played a lot of video games probably aren't working very much, and the people that were working a lot probably weren't playing a lot of video games. All right, so let's do that. So PCH 16. Let's make it rainbow. I like the rainbow color. One. Okay, why not? Two. Okay, don't read too much into the colors. Colors just sort of make it look a little bit prettier. So an example using survey data to predict work hours, or really to model work hours from video game hours. I mean, you can kind of control, you can control both variables here. So I don't know if predict is the best word. I mean, I guess predict for a random person how much they work from how much they play video games. I'll just use the word model. So we're modeling their work hours on their video game hours. All right. So plugin. Here's the plot that I used to generate it. Here's the nice looking plot that I got. Here's the output of the linear model command. So let's do linear model of, and now I'm going to make sure to do work hours tilde video game hours. Okay. Oops. There we go. Now, looks like a negative relationship, which makes sense. This is to be expected since those who seem to work a lot don't play as many video games, and those who play a lot of video games don't seem to work as much. In fact, you know what? Can I maybe resize this a little bit? So it's at about the same scale vertically as it is horizontally. Yeah, that looks a little bit better. And you know what? Should we add the line? Let me use the AB line command. Do this one. This one. Okay. So it's not a super strong relationship, but I mean, we're probably not going to find a particularly strong one in the class survey data, just due to all the randomness. All right, so here's some questions. What did I do? All right, questions one. How many hours of work? How many weekly hours of work predicted from someone who plays, I don't know, 30 hours of video games a week? 35? Let's do 35. Every additional 5 hours of find the predicted see, that's pretty good. I think that's good. All right. You think you can answer those 3 questions? All right, so why don't you answer those 3 questions, and now let's see how you did. All right, so first one, if x equals 35, then we'll get 14 minus 0.07598 times 35. So let's see what that equals. 11.61. So indeed, we just found what the y value right here is. Okay, it's about 11.61. If you play an additional 5 hours, so if delta x is 5, then delta y is 5 times negative 0.07598. Geez. Negative 0.3799. In particular, it's negative. In about 0.38 fewer hours per week, okay? And finally, if x equals 0, the model predicts that y is just the y-intercept, which is 14.27. So students who don't play video games, we just found this point right here. This is about 14, are predicted to work an average of 14 hours per week. Cool. All right, so that's this example. My favorite thing about it is the fact that this is negative, indicating a negative relationship, as was to be expected. And that was, I think, largely a consequence of like these values right here. I don't think these students have jobs. And I don't think these students have time to play many video games. Now, I'm impressed, like some of these students who both work a lot and play. These are my work hard, play hard students, aren't they? Yeah. We're working 40 hours a week and playing like 20 hours a week in video games. How do you do it? Cool. Okay. Thanks for watching, folks. Stay tuned for the next video on 12.2.